lower first column, it tells us all we need to know. Okay, so we'll, and depending on how far we get, either today or Monday, we'll see why that's helpful. Actually, it's probably going to be Monday. But. Okay, so now I can address the big remaining dilemma of our QR iteration. Each iteration is now fast, or faster, but there are too many iterations. Okay. So now we get to the practical QR algorithm. So the idea is, this process that we have in each iteration, QR factorization of a Hessenberg matrix, and then multiplying the factors together in reverse order, still takes too long to converge. Okay. So we want to try to do something about that. So what we know from it is, I can be a little more specific about how slow it could be. That, because we want all the subdiagonal entries of H to go to 0. So an individual subdiagonal entry goes to 0 at this rate. Absolute value of P plus first eigenvalue in terms of size divided by the P eigenvalue. And the trouble is, if this quantity here, if that's near 1, then that's going to be very slow to converge. And you can actually see this if you try this out in MATLAB, that if you notice the diagonal entries that are rather close to each other, you're looking for a subdiagonal entry to go to 0. You can watch it go to 0 as you carry this out. And if these diagonal entries are close that are meant to be eigenvalues, it's going to go to 0 so painfully slowly. Whereas an eigenvalue that's well separated from the rest, that subdiagonal entry goes to 0 very quickly. Okay. So the way we're going to get around this is to use shifts. So the idea is, I'm going to change this process as follows. I'm going to take H, I'm going to subtract some multiple of identity. So this value mu here is what I'll call a shift. And I'll QR factorize that. So shifting the matrix dramatically changes the QR factorization. And then my new H, which I'll call H tilde, I'll do RQ again, and then I'll just add the shift back. Now, what does not change from before we still have the following, that our new H, H tilde, is Q transpose HQ. We had that all along, but the Q that's involved is different. Therefore, H tilde will be different, and that's going to hopefully converge to a triangular or quasi-triangular form more rapidly than before. We just have to figure out what shift are we going to choose. All right. Now what happens here is the new rate of convergence is lambda p plus 1 minus mu over lambda p minus mu. And if we choose the shift well, this will hopefully be smaller and therefore lead to more rapid convergence. Okay. Now, we want to make this as small as possible. How's that going to happen? We want this to be as close to 0 as we can get. Therefore, we want want our shift mu to be close to an eigenvalue. So if we can somehow crudely estimate an eigenvalue and use that as a shift, and we can't use a lot of expense to do this, the hope is we can accelerate the convergence. Okay, so let's see what happens if we were lucky enough to have an eigenvalue as a shift. It's not realistic, but it's going to give us some guidance as to how to proceed. Okay. So if we happen to shift by an eigenvalue, so now I go ahead and do h minus mu times identity is QR factorized. Now, if mu is an eigenvalue, then what do I know about this matrix, h minus mu identity? What property does that matrix have when mu is an eigenvalue? It's singular.
Didn't you say that like the other day? Sorry. I was sitting here, I was like, I know you did. I can't remember what you said.
Even in my first year here, I concluded that students don't have a memory span of more than 5 minutes.
It's also the end of the day, so.
Okay. Yeah, we're going to teach a morning class and I like, it's 8 a.m.
Right, so unless you're teaching at like 10.
Okay.
No, because that's before lunch, and
Right.
you can't kind of spend, and then after lunch, I mean that's shot. So
Right, because you've already eaten.
you're just screwed.
Good enough. So if this is singular, then this has to be singular too. But Q is not going to be singular. Q is an orthogonal matrix. So R is going to be singular. So what that means is R, but here's the other thing. H minus mu identity is going to have n minus 1 linearly independent columns. I mentioned that fact before. And we're assuming H is unreduced. So I should state that assumption, because that's going to be important. Okay. So singular and its rank for both is n minus 1. So R is going to have this structure. So some are triangular, but then this n entry is going to be 0. Because R is going to have only n minus 1 linearly independent columns. It'll be the first n minus 1 columns are independent. The last column is linearly dependent on the others. So you must have a 0 entry here. Okay. Now, we compute RQ. How is RQ computed? Gibbons rotations applied on the right. We're rotating columns. So what will happen, and we stepped through this before, like for instance, first I rotate the first 2 columns. So I get 2 non-zero entries here. Then I rotate columns 2 and 3 to get 3 non-zero entries. Then 4. But then when I'm rotating these columns, I'm only going to get 4 non-zero entries at the most. So that's what RQ is going to look like. I'm still going to have a 0 down here. Then I add the shift back. That only affects the diagonal, and I get a mu. But I still have a 0 down here. So I get decoupling. So in words, what happens is if we shift exact eigenvalue, then decoupling happens in one step. Now, of course, it's not realistic to have an eigenvalue to shift with, but if we have a nearby eigenvalue, then this entry will not be 0, it'll be approximately 0, and this entry will at least be an approximate eigenvalue, bless you, and we can use that as a shift, because we can update the shift every time. So we can get our shift to be closer and closer to an eigenvalue. This entry will get closer and closer to 0. So hopefully we can just perform a few iterations and quickly get the 0 entry and start decoupling and start reducing our problem size. Okay. So more realistically, if mu is approximately an eigenvalue, then our NN entry of R is approximately 0. And then we have our entry in row NN minus 1, the last subdiagonal entry of H tilde is approximately 0. And our NN entry of our new matrix is approximately mu. So, bless you. So this suggests that we use HNN as a shift. So that is what we'll try. It's a heuristic. Well, but we'll use the NN entry of our Hessenberg matrix as a shift on the assumption that it's at least, hopefully, reasonably close to an eigenvalue. And as we carry out an iteration, we'll change the shift to what the new NN entry is. Okay. Now, to give you an idea as to how well this might work, we'll look at a simple example.